Welcome to this presentation on topology-switching coalitional control. Let's get right into it. At the 2018 Winter Olympics in South Korea, the opening ceremony included a display of 1,218 drones flying information. A great achievement and a new world record. However, these drones were all controlled with one central computer, guiding the drones along predefined paths. Now imagine the possibilities if this could be done without a ground station. Formations like these could be deployed anywhere and at any time. In order to make this happen, among others, we need to implement distributed control, such that each drone can make its own individual decisions. However, distributed control comes in many forms, and it is not clear which one is the best suited here. In centralized control, a single controller has all the information about the drones and computes all the control actions for the entire system. This provides the best performance, but also introduces high computational and communicational burden, which is often unnecessary or even infeasible. Especially with a large number of small drones, this approach is not desirable. On the other side of the spectrum, with decentralized control, each drone only has local information to make its decisions. Here, the lack of information degrades performance, or puts a high demand on local sensors. Coalitional control is a halfway approach between centralized and decentralized control, where communication just happens within groups or coalitions of drones. This allows us to make a trade-off between performance and communication costs, and we should be able to find a solution that combines the best of both worlds. One of the main challenges in coalitional control is to find good coalitions. And for the Olympic rings, we will probably be able to find a logical coalition. We could take each ring separately, or maybe also separate the intersections. Either way, we will be able to find something. But what if the drones change configuration? The drones have now moved, and coalitions that seemed logical before will probably no longer make sense, and they will no longer provide the benefit that they did before. Therefore, we need a more flexible approach, which allows changing coalitions over time. And this is exactly what topology-switching coalitional control does, and what I will present today. We denote each possible network topology by lambda, which partitions the system into a set of coalitions, which are clusters connected by enabled communication links. We have considered a linear system, where we can decompose matrices A and B into A lambda and B lambda, which contain the dynamics within coalitions, and AR and BR, which contain the coupling between coalitions. Finally, Yn contains the stacked local measurements of each agent. The controller and observer are designed with the structure as shown on the slide. Feedback gains Kx and Ku and the observer gain L are designed to satisfy the communication constraints imposed by the topology lambda. So, as in the figure, if agent 4 is disconnected, Kx has structural zeros on the entries that connect agent 4 to the coalition of agents 1, 2, and 3. And these same communication constraints are also applied on Ku and L. In this way, no communication between coalitions is necessary to calculate the state estimate and control input. We use an objective function where we weigh both the performance and communication costs over all future time. For the performance, we weigh control performance, control effort, and state estimation performance. For the communication costs, we define a price C for each enabled link during each time step, and this cost is multiplied by the number of enabled links for a certain topology lambda. Now, preferably, we would like to minimize this objective function directly. However, this is not possible, as the objective function cannot be analyzed by the agents. Firstly, because the objective function includes an infinite sum, and secondly, because the agents do not know their own state or the state estimation error. In previous work, Maestre et al. Found a partial solution to this problem. They introduced an LMI formulation to simultaneously design controller gains while also bounding the performance costs, which were part of this objective function. In this work, however, the states are assumed to be perfectly known by each agent. And this method is not trivially extended to also simultaneously design an observer. Therefore, we use this ideal controller design, then separately design an observer, and finally analyze the performance and the stability of the combined observer and controller. Assuming we have an observer, we can use an extended form of the LMI formulation by Maestre et al. To analyze our controlled system. The gains are now already known, but the LMI still provides a bound on the performance costs. However, this bound can still not be calculated by the agents, as the state and state estimation error are still not known. This leaves us to design an observer, which can provide a bound on the state and the state estimation error, such that we can bound the performance costs. To design this observer, we use another LMI-based approach from literature. This approach designs the observer gain such that the state estimation error is bounded by an ellipsoid of a known size. With this, each agent can calculate bounds on the state and state estimation error, and thus a bound on the performance cost can be calculated as well. This gives the following bound on the objective function, where next to the bound on the performance cost, the communication costs are truncated to kappa time steps. The topology is changed to the topology lambda that minimizes this bound on the objective function. We consider that switching between topology takes place periodically, and the frequency at which topologies are switched can be chosen completely independently of the control frequency. So, to summarize, we have designed a coalitional control scheme where topologies are switched online based on the evolution of a bound on the objective function. Between topology switches, we have designed the control and observer gains such that there is no need for communication between the different coalitions, and such that the control system is stable between the switches. Now, this only leaves to prove that the system is also stable over the topology switches. And this can be done. And for details, I'll refer you to the paper, but it's done by proving the total increase over the switches of the quadratic performance term is bounded. And this means that it cannot destabilize the overall system. We have applied these ideas to a simulated platoon of cars, who collaboratively aim at maintaining a desired time headway. Time headway is a distance that varies with velocity, indicated by the time between vehicles. This results in a system, as shown on the screen, where the tracking aerodynamics of each car is coupled with that of the car in front of it. We have simulated a platoon of 4 cars following an imaginary lead vehicle. This lead vehicle is assumed to have a constant speed. The other cars are initialized with an initial tracking error, an initial state estimation error, and with a fully connected topology. Here we see the evolution of the distance tracking error between cars, starting from their initial value and going towards zero. The red lines show the centralized behavior, the yellow lines show the decentralized behavior, and the blue lines belong to our coalitional controller. And we can observe how the topology switches influence the system at 2 and 3 seconds, which is when the topology is actually changed. We can also see that all control methods make the tracking error converge to zero eventually, but that the centralized and coalitional controllers are much faster than the decentralized controller is. The sequence of topologies used is shown here. We allowed topology switches at intervals of 1 second. Initially, the cars were fully connected. After 2 seconds, only cars 1 and 2 still share data. And finally, once the cars were almost at their set point, a decentralized topology was sufficient. With this, the communication cost has been heavily reduced with respect to the centralized control. Furthermore, in terms of reference tracking performance, one can see that the coalitional controller still way outperforms the decentralized controller, and actually closely approaches the performance of the centralized controller. In summary, we have presented the topology-switching coalitional control and observation scheme. This scheme can change topologies online by making a trade-off between performance and communication costs, and is guaranteed to stabilize the networked system. In future work, we would like to explore the possibility of including fault observers into this framework as well, to detect faulty or even malicious agents, such that we can provide a solution also outside nominal behavior. Thank you very much for attending this presentation, and feel free to ask any questions if you have one. To finish this presentation, I would like to acknowledge the contributions of Paula Chanfreut, Riccardo Ferrari, and Maestre.